In this video, we are going to touch upon the topic of ions and ionic compounds. So first up, ions. So to understand what an ion is, we have to remember that in a neutral atom, the number of protons equals the number of electrons. So there's a balancing of charge, and if there's a balance of charge, equal number of positive and negative charges, then the net charge is zero. And of course, you have a neutral atom in this case. Okay. Now, it turns out that during the course of chemical reactions and chemical transformations, atoms can gain or lose electrons. And when an atom gains or loses electrons, then a net charge results. Right? Because you no longer have this balance of positive negative charges. You have either too many negatives or too few negatives to balance out those protons. And so this resulting charged element is what we call an ion. Right? So one example here, we could look at lithium. Okay? Lithium, if it has an atomic number of 3 and therefore has 3 protons. And if you just look at a neutral lithium atom, you then, of course, have 3 associated electrons. What we'll see is that lithium often loses 1 electron to form lithium plus ions. Right? So if we draw out what's happening here, what we're seeing is that lithium is forming a lithium plus, where this lithium plus now only has 2 electrons associated with it. And 1 electron is then given up, and that electron will go somewhere else, and we'll see different places that it could go later on. But for right now, what we want to focus in on is this lithium plus ion, right? This is our ion, and how we denote these ions is very important. We use the upper right corner of the chemical symbol to denote the charge of an atom. So if I just write lithium, right, just lithium like this, because there's nothing listed up in that upper right corner, we are going to assume that I mean neutral lithium with 3 protons, 3 electrons. However, if I write a charge with a sign and a numerical value, right, unless of course that numerical value is 1, it'll just be an implied 1, as is customary in a lot of this chemical symbolism, we are going to then know right off the bat that there is a charge. Okay, so now, lithium plus, when you see that plus sign, we know there's a lithium plus 1, which means lithium that's lost 1 electron, which means it has a plus 1 charge. Okay, and of course we can go the other direction. So another example, we can look at fluorine. It turns out that fluorine oftentimes likes to gain an electron. And when fluorine gains an electron, it forms the F minus ion. Okay, and just a little bit to orient yourself with the terminology here. When we form a positively charged ion, so when we get a positive charge, we call the corresponding ion a cation. Okay? And when we form a negatively charged ion, we will refer to that as an anion. Okay, so anions and cations, they're both ions, but we put that little prefix on there to orient ourselves to tell us whether or not it's a positive or a negatively charged ion. All right, so our first goal here with understanding ionic compounds is to go back to the periodic table, and what we're going to see is the periodic table and the arrangement of the periodic table will actually help us predict the charge that is most likely to form for the different elements in the periodic table. Okay, so this is a very fascinating very fascinating result of the arrangement of this periodic table. Okay? So what I have illustrated here on this slide is the common ions that form for each one of these elements that has their chemical symbol listed in their little square. Okay? And so I want you to take a minute, look at this periodic table, and look for some general trends or patterns. Okay, so hopefully what you see here is that all of these ions in this group 1, remember, are alkali metals, right? All of our alkali metals here will tend to have a +1 charge. If you move over to group 2, all of those ions in that group 2 region tend to have a +2 charge. Okay? Then I'm going to go ahead and move you all the way over, draw your attention way over here to group 15. Notice that these elements in group 15 tend to have a 3- charge. And I should be careful here. All right, our convention when we're writing out charges is to put the number actually before the sign. Okay, so just a convention, right, helps us, remember that we are in fact looking at charges, right? Because there's a lot of numbers that show up describing atoms, right, and their elemental symbols here. And so we can move over here and we see the 16th column. All of those elements in that group 16 elements are having a 2- charge. All of our halogens in group 17 are a -1 charge. And notice that the noble gases here remain neutral. Okay, there's no charge. All right, so ignoring the transition metals for right now, we'll come back to the transition metals here shortly. We see that we could actually we could predict the charge for many different elements in the periodic table by just remembering these characteristics of their groups: +1, +2, -3, -2, so on and so forth. Okay, and so this is pretty neat, right? And so this is what I meant in a previous mini lecture when we talked about the general arrangement of the periodic table, and I said how you could actually use the periodic table to predict the properties of elements. And so this is one example of that. We can use the periodic table and where an element is located on a periodic table to predict the most stable ion that will form. Okay. Now, to give you guys a little context here, so that because I do want you to remember these charges. For all the ones that I've labeled in orange here, I want you to remember these common charges. And so I want you guys to think about where these charges are come from. And it turns out that we can boil all of these common charges down to one basic property. Okay. And if you remember this one basic property, then you can understand and ultimately predict what the common charges for all these guys that we have labeled. Okay. And here's the property. Notice that the noble gases aren't gaining or losing electrons. Right. They don't form ions. Noble gases are happy. Right? That's sort of exactly where they want to be. Okay. Now, turns out that everybody else wants to be like a noble gas. Right? So this is the property I want you to remember. Everybody wants to be like a noble gas. Okay? So just like your average everyday person wants to be like a noble person, have all that money, have all that power, have all that prestige, right? So everybody wants to be like a noble person. Okay? So the same way, elements want to be like a noble gas. All right, but here's the problem, right? You and I are not noble people, right? Oxygen, fluorine, lithium, they are not noble gases. Okay? So what's the best thing you can do if you can't actually be a noble person? Well, you could at least dress and act like them. Okay? So if you could dress and look like a noble person, that's essentially the best thing we can do. So you can put on some nice clothes, whatever it might be. In the context of an element, your clothing is your electrons. Okay? So any given element is going to put on clothing, put on electrons, right? Put on a certain electron arrangement so that that ion or that element and the resulting ion will look like or have the same number of electrons as the closest noble gas. Okay, so what do I mean by that? Let's look at fluorine here. Okay, so remember, if I have neutral fluorine, right, just fluorine off the periodic table, neutral fluorine has 9 electrons. Okay, neon has 10 electrons. Okay, so if fluorine wants to look like that noble gas, then fluorine needs to add 1 electron in order to have 10 electrons and look like neon. Look like neon in terms of number of electrons. Okay? And we notice that if we go down the periodic table below fluorine and we look at chlorine, bromine, iodine, all of these halogens are exactly 1 electron away from looking like a noble gas. So they're in column 17 here, group 17. All they have to do, if you're in group 17, is gain 1 electron, and then you'll look like a noble gas. Okay? If you're over here in group 16, okay, group 16, you have to gain 2 electrons. We'll make that nice and right here. We have to go 1 to look like a halogen, another electron in order to look like a noble gas. If you're in group 15, right, then you have to gain 1 electron to look like group 16, 2 to look like 17, and ultimately 3 electrons to look like that noble gas. And of course, because everybody wants to look like a noble gas, right, we will end up with group 15 elements, assuming a 3 minus charge most commonly. Okay, and so the trend goes on, the trend continues, right? But then if you come over here to the alkaline earth metals, right, what we see then is that, lithium, for example, lithium has in its neutral form 3 protons, of course, and 3 electrons. Okay, so lithium sitting right here, we've got 3 electrons. All right, now lithium, like everybody else, wants to look like a noble gas. Okay, so there's a couple pathways, right? Lithium could add a whole bunch of electrons and end up looking like neon, right? So if he wanted to look like neon, he'd have to go all the way across over this way. You'd have to add 7 electrons in order to look all the way over here, like neon. Okay, so that's a lot of work, and it turns out that that's too much work, and lithium's not actually going to do this. Okay, so too much work. Lithium's not going to want to add 7 electrons. Instead, what lithium's going to do is actually lose an electron and go back up the periodic table and look like neon. Okay, let's clean that up a little bit. So lithium's going to go back up the periodic table and look like helium right up here. Okay, because to look like helium, remember helium only has 2 electrons. So all that lithium has to do is lose, right, minus 1 electron, and then he'll end up looking like helium. Okay, and so we all want to look like a noble person, but we're all lazy. We're going to take the shortest possible, easiest possible path to look like that noble person, right? Elements are the same way. Take the easiest, simplest path to look like that noble gas. Okay, so similarly, if we look at sodium, sodium's going to lose 1 electron to come up here and look like neon. All right, potassium's going to lose 1 electron to come up here and look like argon. Right, rubidium look like krypton, and so on and so forth. Okay, and in the same way, if you go over and look at this second group, our alkaline earth metals. All right, those alkaline earth metals, they have to, of course, lose 2 electrons. They lose 1 electron to look like lithium, and then the next electron to circle back around, and in the case of beryllium, look like helium. Magnesium will lose 2 electrons to look like neon. Calcium will lose 2 electrons to look like argon, and so on and so forth. down the periodic table. Okay, and so that allows us to also understand why aluminum takes a positive 3 charge. Okay, so rather than aluminum gaining 1, 2, 3, 4, 5 electrons, it's easier for aluminum to lose 3 electrons and look like neon. Okay, all right, so that general property of, or general trend in our elements to basically want to look like noble gases allows us to predict the charges of these different elements, and the periodic table nicely groups all of these elements with common charges in the same column. Okay, so very, very interesting thing that's come about here. And the last thing I want to mention before we move on, we talked about these transition metals here kind of right in the center of that periodic table. So these transition metals have, as you may have noticed throughout this lecture, oftentimes they assume different charges, right? So the left-hand, right-hand side of the periodic table, there's only a single charged ion that's formed, whereas with transition metals, what we'll oftentimes see is that there are more than one stable ion. Okay, and so this is something I just want you to sort of file away. I'm not going to ask you to memorize the different stable ions for the different metals, at this point by any means, but I want you to remember that transition metal ions do oftentimes form multiple stable ions. And so this is something that we're going to have to keep in mind, when we're doing chemistry, writing out chemical reactions or naming chemical compounds, as we'll see. So I just want you to file away that fact for right now, and we'll come back to it. When you go into your second semester of university chemistry, you'll spend a fair amount of time talking about these transition metal elements and some of their very unique and fascinating properties, and you'll get a better appreciation for why there are these different stable charge states. But right now, I just want you to remember that they do in fact exist. Okay, so the periodic table here, we're listing all of these elements, common stable ions that are formed. Okay, and so if you have just a single element, okay, just a single element, and it has a charge, we call those monoatomic ions. Remember, mono means one, right? One atom ions, right? And so what the periodic table laid out for us here was all of the monoatomic ions that we would predict to form, okay? And it turns out that ions can come in more complicated forms, okay? And the ones we're going to be looking at here are so-called polyatomic ions. So remember, poly means many, okay? So we have poly, we think many. So many atom ions, right? So really, specifically, we're talking about 2 or more atoms are present. And so we remember, if we have something that, a species that has 2 or more elements present, we have a molecule. Okay? And it turns out that an entire molecule can have an associated charge. And all that means is that this given molecule either has an excess or a deficiency of electrons, and just as we saw with monatomic ions, that will result in a net charge. And we're going to use the exact same convention of putting that charge up as a superscript to the top right to basically denote whether or not we're working with an ion. And so what I've done here is I've listed out for you guys a set of common polyatomic ions, and this is a set of polyatomic ions that we are going to be seeing over and over and over again throughout the course. So I recommend you guys, put these ions on some little flashcards, put the name on the front, put the formula on the back, and just remember them, right? Where it'll save you a lot of time as you move through the course if you just have these quickly memorized, and you can recall them, identify them if they show up in the chemical reactions or chemical compounds. And I just want to point out some general trends here. When you are looking at these molecules, we find that similar to the charges that we saw in monoatomic ions, we're typically looking at +1, -1, +2, -2, And so, it's a general characteristic that you're never going to see, in this course, charges going up beyond, plus or minus 3. Okay, because it becomes relative more and more unstable to have this larger and larger concentration of charge. So the magnitude of charges, even though we've got multiple atoms present, there's still the magnitudes are just the same region, same regime that we've seen before for monatomic ions. Okay. Of course, the difference here is that we've got different groupings of atoms. Okay, and we'll look at them in more and more detail. For right now, I just want you to say, hey, if I've got an H3O with a plus, right, that's hydronium. Okay, if I've got an OH with a minus, right, that's called a hydroxide ion. Okay, and you can go through that whole list. So remember, I'm going to put a little, memorized note on this one. We want you to go ahead and memorize all these common polyatomic ions. Okay, so with that, we're now ready to do our final little application of everything we've learned here. And it turns out that what we can do using these principles of the most likely ion that is to form, that we can look at the periodic table now and predict, we can actually use that prediction to predict the formula for ionic compounds. Okay, so we're going to look at two examples here. The first example I want to look at is a rather pretty example involving the sapphire gemstone. Okay, very pretty gemstone. And it turns out that this gemstone is comprised simply of aluminum cations and oxygen anions. And if you go back to that periodic table, we see on the periodic table that oxygen likes to have a -2 charge. Remember, 1, 2, gain 2 electrons to look like neon. And aluminum will tend to lose 3 electrons to also look like neon. And so alumina has a +3 charge, oxygen has a -2 charge. And now we can use these common charges to essentially predict the ratio of aluminum atoms to oxygen atoms that we would find in the sapphire gemstone. Okay, and so the idea that we use is the idea that when you build up a gemstone or build up an ionic compound, that ionic compound must be electrically neutral. You're not going to have a big sapphire gemstone where every little unit of that gemstone is contributing a non-zero charge, because the whole thing would basically blow apart. You'd be putting so many little charges together, the whole thing would blow apart, right? Bulk matter, right, must be electrically neutral here for building up these gemstones, these ionic compounds. Right? So what we need to do then is predict the ratio of aluminum and oxygen atoms that are required in order to give us this neutral bulk matter. So to do that, what I like to have the students do is actually write out, right? And you can write it out here. We'll do it in black. We're going to write out both of these ions with their charges, okay? And then what you do is you take the charge, but just the numerical value. So in this case, I'm going to take 3 for aluminum, and I'm going to bring it down here and make that a subscript for oxygen. I'm going to take the numerical value for the charge for oxygen, bring it down and make it the subscript for aluminum to give us the following ratio, Al2O3. And what we'll see that in doing that, we've actually balanced the charges, okay? Because notice 2 of these +3 aluminum atoms gives us a total charge of +6, okay? 3 of the 2 minus oxygen atoms gives us 6 negative charges, right? So 2 aluminum +6, 3 oxygen -6, you have a 0 net charge, which is what we were after. So we are then going to predict that the chemical formula for this aluminum oxide that we all know as sapphire is Al2O3. Okay, so kind of a fun little way. This little cross method is a nice little way to quickly build up and predict the formula for these ionic compounds. So before we close here, let's look at one more example. In many ways, it might actually be a simpler example. We're going to look at a less pretty substance, which is called sodium sulfide, comprised of sodium and sulfur ions. Rather than a nice pretty gemstone, these are like some mustard colored flakes, right? So these mustard colored flakes, sodium sulfide, right, has a chemical formula that's once again determined by looking at those common ions. Sodium is a +1, sulfur is a -2, right? So we can do the same sort of game here, and we can say, well, hey, you know, sodium, right, +1, sulfur 2-, right? We're going to take that superscript, right, up here. In this case, for sodium, it's a 1, so I'm going to put a 1 down here. For sulfur, it's a 2, so I'll put a 2 down here. And then we're going to end up with an Na2S. Okay? And of course, you might not even need to use the little cross cancellation rule here, because you might just immediately look at this and say, well, hey, each sodium contributes a +1. I'm going to need 2 of those +1 charges to balance out the -2 charge on that sodium, right? And so that, either way you want to think about it, is completely fine, right? Either way, you're led to a final chemical formula, Na2S for sulfur. Okay, so what we've seen here is we can actually predict the most stable ion by basically looking at that periodic table, looking at the location of that element on the periodic table. And we've seen how elements over here on the right-hand side will tend to form anions, become negatively charged to look like that noble gas. Over here on the left-hand side, we'll tend to find cations, which will be losing electrons to look like that noble gas. And we saw how ions can actually form in the context of molecular species. So you can have groupings of atoms that all come together and have a non-zero net charge. And we saw a list of common polyatomic ions right here. And remember that I asked you to go ahead and memorize these guys. And finally, we saw how we could use these ions in order to predict the corresponding ionic compounds that could form by adding together positive and negative charges. And we saw this method of sort of, you know, crossing those charges and bringing the charges down that we use to solve both of these example problems is a nice, quick, easy way to predict the formula for ionic compounds.